Okay, let's unpack this. Welcome back to the deep dive.
It's good to be here.
If you've ever looked up at the night sky and wondered, what is really going on in this vast, sprawling, cosmic neighborhood we call home, well, this deep dive is for you.
It's a topic everyone sort of knows, right? We all learn the planets in school, but very few truly understand it beyond the basic labels.
Exactly. Our source material today is this fantastic introductory overview, but we're going to take those core facts, the definitions of the sun, the 8 planets, and the smaller objects like moons and asteroids, and we're going to transform them into a fully structured, well-informed understanding.
That's the goal.
Absolutely. Our mission here is not to simply list the planets. It's to understand the mechanics, the chemistry, the physics, and just the sheer scale that defines each planet's environment and its role within the whole system.
We want to help you move beyond the flashcard definition.
Yes, to get to that aha moment that really connects all the dots.
We're basically providing the shortcut to being truly well-informed about our solar system. And to do that, we're going to establish a definitive grand tour itinerary. We're going to move systematically from the gravitational and energetic center outwards.
Charting the vast differences in, chemistry and scale as we go?
Exactly. The differences are staggering.
Which means we have to start with the immense self-sustaining furnace that just dominates everything else, the single object that defines every single rule in this neighborhood.
The sun.
The sun.
Precisely. We have to begin at the core.
Our sources immediately cut right to the chase, and I love this. They describe the sun with this profound simplicity. It's a big hot ball of fire located right at the center of the solar system.
Yeah.
It's the ultimate reduction of a complex star, but it really compels us to ask, what exactly makes it a hot ball of fire? Because it's not like a campfire, is it?
Not at all. And what's so fascinating here is that the phrase hot ball of fire implies simple combustion, like burning wood. But the reality is far more complex and, frankly, fundamentally more powerful.
So what is it then?
This immense heat is generated by nuclear fusion. Deep in the sun's core, the temperatures and pressures are so extreme, we're talking millions and millions of degrees, that hydrogen atoms are literally forced together to form helium.
They're squeezed together.
Squeezed so hard they merge. And this process, it converts a tiny amount of mass directly into a huge amount of energy.
Right. That's Einstein's famous equation, EMC.
That's the one. And it's this staggering, continuous output of energy that generates all the heat and light that bathes the entire system.
So it's not simply on fire. It's literally converting its own substance, its own mass, into pure energy in this continuous, violent process.
And it's been doing it for about 4.5 billion years.
Wow. And that process must require some sort of delicate balance, right? To prevent the sun from either, expanding indefinitely or collapsing under its own massive weight.
It does. It requires a perfect balance. And that internal stability is a key insight. It's maintained by what physicists call hydrostatic equilibrium.
Hydrostatic equilibrium. Okay, break that down for us.
Imagine a constant cosmic tug of war. You have the immense force of gravity from all of the sun's mass, which is constantly trying to pull all that matter inward to crush it toward the center.
Okay, an unstoppable crushing force.
Right. But at the same time, you have the relentless outward pressure created by those continuous fusion reactions in the core. It's a massive ongoing explosion pushing outwards.
So gravity pulls in, the fusion explosion pushes out.
And they are perfectly balanced. This balance is why the sun has remained so stable for billions of years, maintaining its spherical shapes and its very consistent energy output.
So we have this gigantic self-regulating energy generator at the center. But how does that energy get from there, across the vast, vast gulfs of empty space to, say, Neptune?
Well, that energy travels in the form of electromagnetic radiation, which is a fancy way of saying light and heat. And if we connect this to the bigger picture, this energy transmission immediately defines the crucial functions that our source mentions. It gives us light and warmth.
And that really is the so what moment for the entire solar system, isn't it? The amount of light and warmth received defines the environment of every single object orbiting it.
Everything. It's the ultimate gift, as you said. The source really hammers this point home. Without the sun, there would be no life on Earth. That one sentence just summarizes our entire cosmic dependency.
Because everything, from our climate to our chemistry, it all starts with solar input.
It is the absolute necessary condition. And we often discuss the complexity of life, but none of that complexity is possible without the basic physical parameters being met first.
And the sun sets those parameters.
It does. The sun's heat maintains Earth's liquid water, which is a state of matter absolutely crucial for biological processes. And it drives all of our atmospheric circulation, our weather, and our climate systems.
But the sun also shapes the system in ways beyond just heat and light. We really shouldn't forget its gravitational dominance.
Oh, absolutely not. Its immense mass dictates the path and the speed of every single planet, moon, and asteroid we're going to discuss today.
So it's not just the engine, it's what, the ultimate gravitational traffic controller?
That's a great way to put it. Think about it. Even tiny variations in solar activity, like the emission of the solar wind, which is a constant stream of charged particles flowing out from the sun, can have profound effects across the entire system.
And without the sun's gravity, the entire organized structure we're studying would just fly apart into interstellar space.
Instantly. It would just be gone.
So the sun is powerful enough to generate its own energy through fusion. It's large enough to define the orbit of the most distant planet, and it's stable enough to have done this consistently for eons. It literally sets the thermal and physical stage for everything else.
And this leads us directly to the structure of the rest of the solar system. If we're moving outward from that intense central heat source, the environments of the next 4 planets are defined by their immediate proximity to that staggering power.
Their conditions have to be fundamentally different from those farther away.
Drastically different.
Okay, so we must now move past the ignition point, cross the boundary of, 100 million miles or so, and begin our tour with the closest, densest, and rockiest residents, the inner terrestrial worlds.
Let's do it.
Having established the intensity of the sun, the first 4 planets, that's Mercury, Venus, Earth, and Mars, they are the small, rocky worlds verged closest to that immense heat.
And they all share certain characteristics. They have high density, a composition of silicates and metals, and fundamentally, they lack the large gaseous envelopes that define the planets of the outer system.
So we start with the extreme proximity resident, Mercury.
Mercury holds the title of the first planet.
Yeah.
And our source gives us 2 crucial facts right off the bat. It is small, and it is very hot because it's so close to the sun.
How close are we talking?
Its average distance is only about 36 million miles from the sun. For comparison, Earth is 93 million miles away.
Yeah.
So that intense solar radiation is the single defining factor for Mercury.
And that proximity means it just whips around the sun. It takes only 88 Earth days to complete one orbit.
The shortest year in the solar system.
But that closeness also contributes to its extreme thermal conditions.
It does. And the fact that it is small is equally significant here. Because Mercury has a low mass, that translates to weak gravity.
Which means it couldn't hold on to an atmosphere.
Exactly. It was unable to hold on to any significant atmosphere, and what little may have existed was just blasted away over billions of years by that intense solar wind we mentioned.
Okay, so without an atmosphere, there's no blanket to trap heat, and there's no circulation to distribute it around the planet.
Precisely. And this leads to massive, unbelievable thermal extremes. The side of Mercury facing the sun can reach well over 800 degrees Fahrenheit. That's hot enough to melt lead.
Wow.
But then, because it has virtually no insulating atmosphere, the night side plummets to several hundred degrees below zero.
So you have these 2 extremes on one tiny world.
You end up with a world defined by the brutal extremes of scorching heat and crushing cold, simply due to that closeness combined with the lack of an atmospheric buffer.
It's a study in contrasts. A small world, a short year, and the most extreme temperature swings imaginable. But here's where it gets really interesting, because we move just one step further out to the second planet, Venus. And our source throws us a fundamental paradox.
This is a crucial nugget of knowledge for you, the curious learner. This is what separates a basic understanding from a deep one.
Because the source says that while Mercury is the closest, Venus is described as being even hotter than Mercury.
Which should not be possible.
Right. It violates the basic expectation of the solar system structure heat should fall off with distance. If Venus is almost twice as far from the sun as Mercury, why on Earth is it hotter?
We have to look at the second descriptive fact the source gives us about Venus. It's covered with thick clouds. This is the key that unlocks the entire mystery.
Yes, it's the atmosphere again.
It's all about the atmosphere. Mercury lacks a substantial one. Venus possesses an atmosphere that is nearly 100 times denser than Earth's. And it is overwhelmingly composed of carbon dioxide, those thick clouds you mentioned being made of sulfuric acid.
Ah, okay. So this is the ultimate example of the runaway greenhouse effect. The carbon dioxide atmosphere lets sunlight in, but then it traps the resulting infrared heat radiating off the surface with immense efficiency.
Immense is the right word. Precisely. That thick atmosphere acts like an immense, heavy blanket, trapping heat so effectively that the average surface temperature stabilizes at over 900 degrees Fahrenheit.
900 degrees.
Making it by far the hottest planet in the system. The proximity to the sun started the process, sure, but the atmospheric chemistry completed the transformation. It created a superheated pressure cooker.
It's a really sobering lesson in planetary climate. Venus is essentially Earth's cautionary tale, showing what can happen when a terrestrial world, through its early geological processes, locks up way too much carbon in its atmosphere.
The planet is defined by the destruction wrought by its own environment.
So what stands out here is that Venus is this profound example of how atmosphere, not distance alone, controls a planet's temperature.
Absolutely. So we've established the scorcher in the oven. Now we move to the third planet,
Earth, which the source describes simply as our home. But it's afforded a truly unique status, explicitly stating why. Earth is special because it has air, water, and life.
And that trio of elements is completely unique among the 4 inner planets we're discussing. Earth manages to exist in that precise orbital region that scientists call the Goldilocks zone.
Not too hot, not too cold.
Exactly. Not too hot like Venus, not too cold like Mars. It's in this zone where the combination of its distance from the sun, its mass, and its gravitational capture of essential gases creates the conditions necessary for liquid water to be stable on the surface.
And the Goldilocks zone is really all about maintaining liquid water, which, as the universal solvent, is the foundation for life as we know it. But distance isn't the only factor. Our air, our atmosphere, provides the necessary shield.
It's a crucial component. The atmosphere not only maintains moderate temperatures, but coupled with Earth's powerful magnetic field, it provides a vital layer of protection.
From what?
From that solar wind. This magnetic field deflects those charged particles we mentioned earlier, preventing our atmosphere from being slowly stripped away into space.
Which is a fate we believe befell Mars.
That's right. Mars lost its magnetic field, and then it lost its atmosphere.
So Earth is defined by its careful balancing act. The right distance for warmth, the right magnetic field for protection, and the right atmospheric composition for a breathable environment where water can persist in liquid form.
It is defined by its hospitality. It's a sanctuary wedged between 2 scorching, hostile environments.
And that brings us to the 4th and final inner planet, Mars, our dusty, smaller neighbor.
The red planet.
Yes, it's defined entirely by that visual characteristic referred to as a red planet because its surface looks red.
And that striking hue, that visual identifier, is derived directly from its geology. The surface is incredibly rich in iron oxide, which is just the scientific name for common rust. Rust. And this tells us a lot about its past. The presence of iron, of course, but critically, the processes of oxidation that would have required water and a thicker atmosphere at some point in its distant history.
So its common name links directly to the geological reality. While Mars is a cold, dusty desert today, the presence of all that rust suggests a very different, wetter past.
It absolutely does. Compared to Earth, Mars is smaller, it has lower gravity, and a much, much thinner atmosphere. We're talking less than 1% of Earth's surface pressure.
And that low gravity meant it couldn't hold on to its thick atmosphere, especially once its internal core cooled and its magnetic field diminished.
Right. And without that magnetic shield, the solar wind just went to work, slowly eroding the remaining atmosphere and stripping away the conditions needed to sustain liquid water on the surface.
So we've moved systematically from the scorcher, Mercury, to the oven, Venus, the sanctuary, Earth, and finally to the cold, rusty desert of Mars.
You see a clear pattern: small, dense, rocky, and heavily defined by their immediate proximity to the sun. But they differ profoundly based on their atmospheric evolution.
We've established the terrestrial core, but now we are facing a transition so massive, both in scale and in chemical composition, that it fundamentally changes the definition of a planet. We hit the Great Divide.
And we must prepare to cross the frontier where rock and metal give way entirely to gas, ice, and truly titanic proportions.
Okay, so we've finished our survey of the inner volatile poor planets. Now we confront the first major structural boundary in the solar system. Our source describes it as a big empty space called the asteroid belt, found after Mars.
That description, a big empty space, is a bit misleading, but it does capture the immense significance of the region. It represents the enormous distance, and more importantly, the chemical line that separates the terrestrial planets from the colossal giants.
A chemical line? What do you mean by that?
Well, this belt is in the region that scientists sometimes refer to as the frost line or the snow line.
A frost line.
Right. Closer to the sun, where the inner planets are, the intense heat means that volatile compounds like water ice, methane, and ammonia just can't condense into solid forms. They're gases. So only rocky materials and metals can clump together.
But beyond the belt?
Beyond the belt, it gets cold enough for these ices to be stable building materials. And that is the fundamental reason why the inner planets are rocky and the outer planets are so rich in ices and gases.
So the asteroid belt itself is populated by these, remnants that weren't able to coalesce into a planet?
Exactly.
Huh?
Largely due to the incredible gravitational interference of the very next body in our tour.
Ah, so the belt is not actually empty.
Not at all. It's estimated to contain millions of objects. But the structure of that belt, and the reason it never became a fifth terrestrial planet, is fundamentally due to the gravitational dominance of Jupiter. Jupiter is the ultimate gravitational shepherd. It stirs up all the material in the belt, and its gravity prevents it from accumulating successfully into a planet.
So once we cross that belt, the rules of scale just change entirely. We are introduced to the fifth planet, Jupiter, which is immediately defined by the source as the largest planet in our solar system.
And that one fact underpins everything else we know about it. Jupiter is so large, you could fit every other planet in the solar system inside it, and you'd still have room left over.
That's hard to even imagine.
It has more than twice the mass of all the other planets combined. And this scale, this sheer size, dictates its composition, its weather, and its effect on everything else in the system.
The scale is almost incomprehensible. But what's even more defining than its size, I think, is its signature feature. It's an object you can spot with relatively simple telescopes.
The Great Red Spot.
Yes, a source says it has a big red spot, which is a huge storm.
And we need to give this storm the reverence it deserves. The Great Red Spot is not just a huge storm. It is a permanent, immense anticyclonic weather system that has been continuously observed since at least the 17th century.
For centuries, a single storm. And to bring that scale back to something we can understand, back to Earth, the Great Red Spot is currently large enough to swallow our entire planet whole.
Maybe even 2 or 3 Earths, depending on its current dimensions, which do fluctuate.
The fact that a single storm on Jupiter is larger than the entire solid body of our home planet is just, it's mind-boggling.
And what does a storm that lasts for centuries suggest about the atmosphere of a gas giant?
I mean, I have no idea. What does it suggest?
It tells us two very important things. First, the lack of a solid surface means there is no friction to slow the storm down and cause it to dissipate, unlike on Earth where storms lose energy over land.
So it just keeps going.
It just keeps churning. Second, the massive internal heat that Jupiter generates, combined with its incredibly rapid rotation, Jupiter has the shortest day of any planet, spinning once every 10 hours.
10 hours.
It creates these titanic atmospheric shear forces that continuously feed energy into the storm system, keeping it going.
It's a dynamic monument to planetary chaos, constantly in motion, yet permanently in place. The scale of the planet also must explain its dominance over its surrounding environment.
Yes, and the final metric of Jupiter's dominance is stated very clearly in our source. Jupiter has more than 70 moons.
More than 70.
This vast satellite system, which includes 4 major moons, Io, Europa, Ganymede, and Callisto, often called the Galilean moons, stands in stark contrast to Earth's single moon.
That immense gravitational power allows it to capture and hold dozens of smaller objects, turning Jupiter into a miniature solar system all by itself.
It's also, crucially, the system's gravitational shield. It helps to deflect or absorb comets and asteroids that might otherwise threaten the inner worlds, including us.
So it's our protector.
In many ways, yes. It is truly the king of the system, defined by its titanic scale, its permanent atmospheric chaos, and its huge retinue of orbiting companions.
Okay, so moving on from the king, we come to the 6th planet, Saturn.
Saturn.
If Jupiter is the system's king, Saturn is undoubtedly the system's visual masterpiece. It's famous for its beautiful rings.
That visual identity is crucial. No other planet, when you see it through a telescope, provides such an immediate sense of awe and complex geometry.
And the source gives us a wonderful and very specific detail about the composition of these famous rings. They are made of ice and rock.
And this detail is pivotal. It really solidifies that chemical shift we crossed at the asteroid belt. We are now far enough from the sun that these components are predominantly icy water and rock particles, orbiting in millions and millions of individual paths.
And these rings are dynamic. They're not static, are they?
Not at all. They are incredibly thin. In some places, only tens of meters thick, but they stretch for hundreds of thousands of miles across.
Unbelievably wide, but razor thin.
Exactly. And the complex patterns within them, the gaps and the shepherd moons, are all created by the gravitational interactions of Saturn's own moons, which continuously sweep up or push the material around, maintaining that delicate, beautiful equilibrium.
It really emphasizes the difference between the terrestrial rocky inner worlds and these gas giants. While Jupiter is characterized by its storm and sheer mass, Saturn is defined by this incredible, beautiful complexity of its dynamic, icy structures.
And while it's visually spectacular, its composition is actually quite surprising. Despite its colossal size, it's the second largest planet. Saturn is the least dense planet in the solar system.
Least dense.
It's largely composed of hydrogen and helium, so light that if you could find a bathtub large enough, Saturn would actually float.
That's a perfect analogy. It captures the difference between a dense, small, rocky world like Earth and a massive, puffy world like Saturn. We've cataloged the 2 largest and most massive giants. Now we have to prepare for the long, cold haul even further out.
To the icy, strange twins in the true outer reaches.
Right. We now move beyond the most massive gas giants, and we enter the final frontier of the classical solar system. These distant worlds, Uranus and Neptune, are known as the ice giants.
And that's a key distinction. While they're also massive, their composition includes a much higher percentage of volatile ices, like water, methane, and ammonia. This differentiates them from the predominantly hydrogen and helium composition of Jupiter and Saturn.
And the sun's influence here, well, it's still controlling their orbit, must be severely diminished in terms of warmth and light.
It's a dim, distant star from out there. And we start with the seventh planet, Uranus.
Uranus is defined by three key characteristics from our source. Its position, its appearance, which is described as blue-green in color, and its unique motion. It spins on its side.
And that unique motion is the true geometric peculiarity of Uranus. So it makes it so strange.
How so?
Well, while most planets spin roughly perpendicular to the plane of the solar system, you can imagine Earth standing more or less upright as it orbits. Uranus is tilted by a staggering 98 degrees.
98 degrees, so it's basically knocked over.
It literally rolls around the sun like a ball. It spins on its side.
What could have caused that?
That anomaly strongly suggests a catastrophic event early in its history, most likely a massive collision with a protoplanet, something maybe the size of Earth, that just fundamentally altered its rotation axis.
And that tilt must have enormous implications for its environment, particularly its seasons.
Oh, the seasons are extreme. If it's spinning on its side, think about it. The North Pole, for instance, must face the sun for a very, very long time, followed by an equally long period of total darkness.
And how long is that?
Well, since Uranus takes 84 Earth years to complete a single orbit, the consequence of spinning on its side means that one pole can experience continuous daylight for 42 Earth years.
42 years of summer.
Followed by 42 years of continuous darkness, a 42-year-long winter. This leads to climatic extremes that are just difficult for us to even imagine.
So Uranus is not just strange in its tilt, it's strange in its temporal definition. And what about the color? The source mentions its blue-green appearance.
That color comes from the presence of methane gas in its atmosphere. Methane is very good at absorbing the red wavelengths of sunlight, which allows the blues and greens to be reflected back into space,
giving it its distinctive cyan hue.
Exactly. And that chemical identifier marks it clearly as an ice giant, distinguishing it visually from the yellows and oranges of Jupiter and Saturn.
Okay, so we move from the sideways spinner to the absolute edge of the planetary family, Neptune.
Neptune is the eighth and last planet confirmed by our sources, and its description focuses entirely on the consequences of its extreme distance from the sun. It's far away, cold, and windy.
Let's try to contextualize that distance. Neptune orbits nearly 30 times further from the sun than Earth does.
30 times. At that distance, the sun appears as just a tiny bright star, giving it minimal solar input. And this, of course, explains why it is universally cold.
How cold are we talking?
Intensely cold. Temperatures in its upper atmosphere hover around negative 350 degrees Fahrenheit.
Minus 350.
However, the accompanying detail that it is windy is a truly counterintuitive insight. How can a planet so far from the sun, so incredibly cold, be so dynamic?
Right. You would expect quiet stagnation, not violent weather systems.
This is where we learn that these outer worlds have significant internal heat sources of their own, left over from their formation. And it's the combination of this intense internal heat trying to escape, the planet's rapid rotation causing massive Coriolis forces, and the extreme cold of the upper atmosphere.
That creates staggering pressure differences.
Exactly. And those pressure differences drive the fastest wind speeds ever recorded in the solar system. They often reach supersonic speeds of over 1,200 miles per hour.
1,200 miles per hour? That's faster than the speed of sound on Earth.
It's incredible. So the extreme distance results in extreme environmental conditions. It's not just quietly cold. The distance leads to these dramatic, violent weather systems.
We've traced the planetary family from the inner scorchers all the way out to the outer icy speed demons.
We've really spent this time charting the sheer scale of the system. We started where a year is just 88 days, and we've ended where a single orbit takes 165 Earth years.
The movement between the inner rocky core and the massive gaseous outer shell is the defining structural element of our entire system.
It is a vast, interconnected family, and now that we've charted the static components, the composition and environment of the 8 planets, It's time to talk about the dynamic components.
The things that keep the system constantly and predictably in motion.
Right.
Okay, we've established that the solar system consists of the sun and the 8 primary planets. But we must not forget the extensive supporting cast, specifically the moons.
The definition provided by our source is very functional. Moons are smaller objects that go around the planets. They are sub-satellites, really, systems within the larger system, all bound by the gravity of their parent planet.
But the diversity among the moons is just huge, and this is where the system gets incredibly complex and interesting. The source emphasizes this variety. Earth has 1 moon, while Jupiter has more than 70.
And that comparison really highlights the immense diversity and the varying gravitational capabilities of the parent planets. Earth's single large moon is absolutely vital to us. It's responsible for stabilizing our planet's axial tilt and for driving our tides.
It's a massive, relatively isolated presence.
It is. But then you look at Jupiter with its 70-plus moons, and you realize that the planet's gravitational well is so deep, it can retain everything from tiny captured asteroids to 4 massive satellites that actually rival the size of the planet Mercury.
And those 4 Galilean moons, they tell a really dynamic story on their own.
They absolutely do. Consider Io, which is Jupiter's innermost major moon. It is the most volcanically active body in the entire solar system.
More than Earth.
Far more. And it's not heated by the sun. It's heated by the tidal forces exerted by Jupiter's immense gravity. The planet is constantly stretching and squeezing Io's interior, generating enormous heat from friction.
So Jupiter's little system is powered by mechanical friction, not by solar radiation. And then there's Europa, right? Where that same tidal heating maintains a massive subsurface ocean.
A huge ocean beneath a thick layer of ice. These moons are not just passive orbiting rocks. They are active, dynamic worlds powered entirely by the scale of their parent planet.
So the sheer numbers 1 versus more than 70 demonstrate that the solar system is actually a collection of these planetary subsystems.
That's a perfect way to look at it. The closer you are to the central mass of the system, the less dominant the planet is over its own neighborhood. But the further out you go, the more dominant the planet becomes in shaping its own tiny system.
And all of these objects, the planets, the moons, the asteroids, they are all defined by one constant. They are always moving.
That is the essential dynamic element. The solar system is described by the source as always moving. And this movement of the primary bodies is highly regulated. The planets travel around the sun in circles.
And the source gives us the crucial technical term for that controlled motion.
Yes, this is called an orbit.
An orbit.
We should probably expand on the nature of that orbit, though. While the source simplifies it to circles, in reality, planetary paths are ellipses. They're slightly flattened circles. This was Kepler's great insight.
So they're more like ovals?
Slightly oval, yes. An orbit is the perfect path that's defined by the balance between the sun's constant gravitational pull and the planet's innate forward momentum, or inertia.
Why does knowing it's an ellipse matter to you, the listener?
It matters because of the concept of speed. In an elliptical orbit, a planet's speed actually changes throughout its year. When Earth is closest to the sun, at a point we call perihelion, it moves faster.
And when it's farthest away?
When it's farthest away, at aphelion, it moves slower. Distance dictates speed, and that is a fundamental component of the system's motion.
And to make the abstract concept of an orbit relatable, we have a perfect human metric. It takes Earth 1 year to go around the sun.
That is the defining temporal unit for human civilization, born directly from our own orbital mechanics. But this one fact immediately implies a massive comparative scale for the rest of the system. It connects distance, speed, and time.
Right, so if we go all the way back to Mercury, which is extremely close to the sun, its orbital path is short, and because it's closer to that immense gravitational pull, it must move incredibly fast to avoid falling into the sun.
Which results in a year of just 88 days.
But conversely, let's look at Neptune again, which is described as being far away. Its orbital path is absolutely colossal, and its relative speed is much slower because the sun's gravitational pull is weaker out there.
And as we noted, its journey around the sun takes 165 Earth years.
So the implication here is profound. Your definition of a year is a direct function of your orbital position. For a hypothetical resident of Neptune, a single birthday would span generations of human life.
The sheer distance is governed not only temperature, but also the very progression of time relative to the sun.
It's this constant, regulated movement, this precise and predictable dynamic dance that's powered by the central mass, that defines the life and structure of the solar system.
It is the system's perpetual clockwork.
It's an intricate, vast, and complicated neighborhood, and understanding these dynamics is really the final piece of the puzzle.
I think so.
Wow. We started with what really looked like a simple list of high-level facts. A hot ball, 8 planets, some circles, and through this deep dive, we've uncovered a system that's defined by immense chemical and physical complexity.
We really have. We've moved from the engine of the sun, explaining nuclear fusion and hydrostatic equilibrium, through the dense, rocky worlds, resolving that paradox of Venus's heat via the runaway greenhouse effect.
And then we charted the vast scale of the gas giants, understood the long-term mechanics of Jupiter's storms and Saturn's rings, and we concluded with the extreme, tilted, and windy ice giants at the very edge.
It's been quite a tour.
And most critically, I think we understood the geometry and the chemistry that separates the terrestrial worlds, the rocky, dense, small ones, from the giants, the gaseous, icy, massive, low-density ones.
And that structured understanding, knowing the why behind the facts, that is the shortcut the curious learner seeks.
It grounds our understanding of how big and wonderful the universe is, starting right here, right at home.
Indeed. We've established that the entire solar system is always moving and constantly revolving in its defined, slightly elliptical orbits. This constant motion implies stability, but it's only a dynamic, ongoing stability.
If everything is always in motion, then nothing is truly static. It's a system of competing forces in this constant, delicate balance.
And that is the final provocative thought we want to leave you with. The forces that hold the solar system together, gravity, fusion pressure, orbital mechanics, they're immense, but they are also always operating.
So, what does this endless dynamic motion imply about the long-term fate of this beautiful family?
Exactly. As you encounter information about things like orbital perturbations or the eventual expansion of the sun into a red giant, remember that the constant motion we observe today is the very engine that will drive the system's changes in the unimaginably distant future.
A perfect thought to end our dive into the mechanics of our solar system. Thank you for joining us on this tour.
Thank you.
We'll catch you on the next deep dive.